This is Becca Taylor, Claire Offer, Sarah Frey, as in French fry, and Wyatt Self. We will be talking about diffusion, mass transport by atomic motion. This is for Material Science 321.
We will first begin by doing an overview of diffusion, followed by an example of how diffusion plays into thin films manufacturing.
Two types of diffusion are interdiffusion and self-diffusion. Interdiffusion occurs in an alloy where atoms migrate from regions of high concentration to low concentration, such as these birds which are flying from a place on the beach with high bird concentration, something that would seriously scare ornithophobics like me, to a place of low bird concentration, such as where the camera is. Imagine that some of these birds are different, such as in an alloy where the atoms are not all the same. In an elemental solid, all the atoms are the same but migrate within the solid as time goes on, similar to those tumbleweeds blowing past. But then the wind will change and they will move to another place, similar to the atoms migrating in the self-diffusion. Mechanisms for diffusion are different for gases and liquids and solids. Solids experience interstitial and vacancy diffusion. Interstitial diffusion is where smaller atoms diffuse between atoms, such as the baby elephant, which has diffused between the big elephants. Imagine that the baby elephant is a small atom which can move all around the bigger atoms. As Lena Dunham says, people always think that I'm not going to fit in at first, but I always do. I always fit in, just very subtly. Vacancy diffusion is like a kid's toy where the picture is broken into moving squares with one square missing. The atoms exchange with the vacancies and can move from one vacancy to another. The rate of vacancy diffusion relies on the number of vacancies. If two of the squares from the picture were missing, then it would be much easier to get the configuration desired. Also, the rate depends on the activation energy needed to exchange atom positions. Of the two, interstitial diffusion is faster. Liquids and gases diffuse by Brownian motion. Brownian motion, which translates to leaping in Greek, is the random motion of particles in a fluid. The motion is from collisions with other atoms or particles in the fluid. It is random like the fuzzy screen seen here.
Now we're going to go over some factors that influence diffusion. We have species, temperature, and other pathways for diffusion. Starting with species, we can see that smaller molecules are more mobile due to interstitial movement. From this equation, we can see that velocity is inversely proportional to mass. For temperature, as the temperature increases, the energy increases and allows molecules to move faster. Here's a graph of the diffusion coefficient versus temperature. We can see as temperature increases, so does the diffusion coefficient. Other pathways for diffusion also affect the diffusion coefficient. Some examples are microstructural features like grain boundaries, dislocations, and surfaces. Here below, we can see an image of a grain boundary. Some factors that will make faster diffusion are open crystal structure, secondary bonding, smaller atoms, and lower density. Some factors that will contribute to slower diffusion are closed pack structures, covalent bonding, large atoms, and large density.
There are two different types of diffusion. The first type is steady-state diffusion. Steady-state diffusion is diffusion in which the rate is independent of time. The rate of diffusion is known as the flux, which has the units of moles or mass over area per time. Flux is proportional to concentration gradient. This can be shown in Fick's first law, in which flux equals the negative diffusion coefficient times the concentration gradient. If diffusion is linear, the concentration gradient can be reduced to the concentration at location 2 minus the concentration at location 1 over the distance between those locations. The second type of diffusion is unsteady state diffusion. Unsteady state diffusion is diffusion in which the concentration is dependent on both location and time. This is represented by Fick's second law. The solution to Fick's second law has the error function in it. You have to use tables to find the solutions to the error function and the values within. Fick's second law also has the location at concentration at a position and time. It also has the initial concentration within the system and the surface concentration of the system.
So a specific example of diffusion being used in industry is for thin film manufacturing. The purpose is to selectively include impurities in very pure or pre-doped silicon. This can create N or P-type semiconductors, and these N and P-type dopants can form junctions. This allows for precise control of the dopant concentration at any distance from the surface. This is a two-step process, and it is unsteady state. The first step is pre-deposition, which provides a high concentration source, which is followed by the drive-in, which diffuses dopants into the wafer. So our example first starts with the pre-deposition step, which, as we mentioned before, diffusion is a function of both activation energy and temperature, given by this equation, and d naught is a constant for a given molecule. And in this case, for boron, we have a d naught of 0.037 and activation energy of 3.46 EVs. And we're going to use a temperature of 950 degrees C. So solving for the diffusion coefficient at this temperature with this molecule, we find our diffusion coefficient of 2.018 times 10 to the negative 16th centimeters squared per second. As you can see, this is very small because we're diffusing into a solid. Next step of pre-deposition, we have to find the amount deposited on the surface. And so Q naught is how much we have at the surface, and CS is the amount already deposited into the wafer of a different element. So solving for this, we can find how much there is on the surface of our wafer, which is a very high number because this is molecules per centimeters cubed. The next step, the drive-in, which is done at very different conditions. We first calculate the concentration at the surface using this equation here. And so, because we're looking for the concentration at the surface, our x term is 0, and our diffusion coefficient is the same as previously calculated, giving us a surface concentration of 2.34 times 10 to the 18th. Now to calculate the junction depth, we need to use our new conditions, which is 1100 degrees Celsius and for a much greater time of 10 hours. Our junction depth equation can be seen here, and solving for it, we find that at 0.68 micrometers, we will have the concentration of our dopant that was just added equal to the previously doped concentration of 0.68 at 0.68 micrometers. And this concludes our material science example.